Hello students, welcome back. Let us resume our discussions in exponential equations. Let's go down to this, and please recall that we went through first three problems here. And all these are quadratic type. That is, each of these equations can be reduced into a quadratic equation of exponentials, and then we can solve it as usual. Factor it while keeping the right hand side equal to 0, solve for the exponential, and then taking the logarithm. Now let's go to these final two types of problems, and these are both linear type. So quadratic versus linear, these should be a little bit easier. As far as algebra is concerned, it is easier. Except that we have some weird numbers here and there, and down there is even worse. Okay, let's go down here and let's try to solve it. Alright, did I say this is linear? How do you solve a linear equation? Step 1, denominators. Step 2, parentheses. Step 3, like terms. Okay? I don't think you'll have to worry about like terms here because you have only one t term here. So no like terms. But otherwise, you have to do what you used to do. First step, remove the denominator, multiply out. Next step, break off the parentheses, but looks like I can simplify this before doing that. Remove 2 zeros here and 2 zeros there. That's equivalent to dividing 100 from both left-hand side and right-hand. So no problem there, it's just a routine simplification, and small numbers are easier to deal with than large numbers, so it's a step up. Now let's go to step 2, real step 2, break off the parentheses. 5 equals to 2 plus 2 times 25, that's 50, exponential of negative 0.3t. Therefore, 50 exponential of negative 0.3t is equal to what? 5 minus 2 is 3, isn't it? That's 3 over 50, and that's 6 over 100, so 0.06. So what do we have here? We successfully solved this linear equation with respect to exponential. Now we identified exponential. How to find t? I have to remove this exponential by taking the inverse function. So how do you do that? We take the natural logarithm of both. Log and exponential cancel each other out. Equals to log of 0.06, and we're almost there. Divide away by this coefficient and we're through. And if you punch into calculator, you're going to get what you want. Let's see, what is this? Natural log of 0.06 over negative 0.3, and you're supposed to get this. Check your computation. If you use TI calculator, then ln computation is in second floor somewhere. One more thing. If I use Mathematica, ln and log turn out to be the same. Okay, ln, log turn out to be the same. And the reason is because Mathematica is based upon complex number system, so everything is log. ln is strictly for real number system only. But here in college algebra, we don't deal with a lot of complex numbers and so on, so we don't do log, we just use ln. So if you're using handheld calculator, just use ln. Do not use log, unless you know what you're doing. Okay, we went through one problem like this, and here we have almost identical problem here. Same structure, different numbers. Now, can you do the same thing here? You should be able to do that, so please go ahead and do this. Stop the playback and try it on your own. Did everybody try? Okay, let's assume everybody did it, and let's go ahead. Okay, that's a problem, all right. Step 1, denominator. So okay, here we go. Flip the denominator to the other side by multiplying it both to left hand side and right hand side. And break up the parentheses. Did I do everything right? So 45 minus 10 is 35. So exponential is equals to 35 over 25, which is 7 over 5. Both are divisible by 5. And in terms of decimal, what is it? That's multiplied by 2, then that's 10, and that's 14. Yeah, 14 over 10, so it's 1.4. Okay. Please check the computation. I use my mental math, so I don't trust myself completely. What did I do in this answer key? Yes, 1.4 is right. Okay, 1.4 is right, so I did everything right. Okay, all right. Okay. First step is done. We found out the exponential. Now let's take the natural logarithm of both, and we can find out what t is. Log of exponential, which will just cancel each other out. And of course, you can use your calculator to find this one out. Go ahead and do that. What do you get? And I'm getting negative 0.84, approximately speaking. Okay. So do you feel all okay about these kind of problems? Now, why do we study these kind of problems? These two types of problems down here, problem D and E, those kind of problems are called logistic models. It looks like this. Let me expand the font a little bit more. It is called a logistic growth model. And it explains population growth in a closed environment. For example, if you want to measure how the population of your bacteria is growing in your lab, it follows this kind of problem. And T is time. And well, depending upon what kind of bacteria, T can be measured in hours or sometimes days. Now, if you want to measure how a certain mammals like deers or wolves and those kind of things are growing in a certain closed environment like an island or something, again the same problem here, of course with different numbers. T is going to be measured in years. How a disease is spreading out in a certain environment, like nowadays with COVID and everything. In that case, T will be measured in days, probably. Again, the same function is being used. How political views or some news, sometimes fake news, are spreading around in social network, again, the same function. Here, the numerator A is the mature population, the stabilizing population, and this value B and K k are related to where we start, the initial population, and how quickly disease is spreading, or the news is spreading, or population is growing or stabilizing. Here's an example. Let's plot this. Okay, if I plot from -5 to 5, we get a nice exponential growth. Like this. Initially pretty slowly, but after a while, growing rather quickly. Let's go from -20 to +20. Now the growth is slowing down here. Let's go a little bit further. Oh, I meant 30. Slowing down even further, do you see? Let's plot it this way. Now you can clearly see that this logistic growth function has two horizontal asymptotes. Y equals to 0 to the left, and y equals to the numerator, in this case 500, to the right. That's going to be the mature population. So 500 units, whatever unit is the mature population for this particular model. So particularly long time later, sufficiently long time later, then we can assume we reached the mature population. And long time ago, theoretically we're going to start from just one bacterium or maybe really small number. So to the left we get horizontal asymptote of 0. And -t meaning past. So for example, 80 days ago from the moment right now I began to measure, or 16 hours ago, things like those. So negative values here make perfect sense. As you see down here, we got -t. It shouldn't bother you. -t means some time ago. So in this case, how many time units later the population reached 200 units? You're solving for t, and it turns out this kind of exponential equation. We're going to talk a little bit more about logistic modeling and this kind of function in the next week, because we're going to deal with exponential and logarithmic modeling in module 14, and that's where we're going to study all these again. For now, let's look at those in terms of just algebraic equations, or excuse me, not algebraic equation, algebraic method to solve these equations. These equations are exponential, transcendental equations, but the method is algebraic. Okay, so much for the first type, exponential equations. Let's stop here, and we'll meet again with logarithmic equations in the next video.